Lesson number 1, page 188, number 7. You have a plane that's climbing up on the right and a plane that's headed down on the left. And basically you're going to be calculating the difference in the amount of work done on each of these planes. Now basically there's 3 forces acting on these planes. There's the downward weight force, which is F sub g. And they tell us the weight of the plane is 5.9 times 10 to the 4th. So this is the same plane over here. Has a downward weight force 5.9 times 10 to the 4th newtons. There's a lift force due to the wind going above the plane, the wings of the plane, and the wind going below the wings of the plane. The air on the air pressure above the wings is actually lower, and that puts in a lifting force this way. We're not told how much, but there's the same lift force over here acting on this plane. And then the engines of the plane is thrusting it forward. So there's a forward force called T for thrust. That's what the jet engines are thrusting it forward with so much force. And there's that same thrust force acting over here. And then remember, the forward distance, x, is shown here in yellow.
Yeah, I was saying that like one you can do the normal force for T in addition to G, whereas one it's T and then you're subtracting. One is fighting gravity, one isn't.
Yeah,
True.
The right one is fighting gravity, therefore
So you automatically know the right one has to be greater.
it would have to be doing more work. Because they're traveling the same distance and they weigh the same.
Right. Let's take a look at, let's compare both of them. We know that if you want to go and calculate work, the general formula for work is work equals the force times the forward distance times the cosine of the angle between the direction of the force and the direction of the forward distance. Yes?
Yeah.
Now, if both jets are applying the same forward force, and both jets move forward the same distance, how's the difference between, this guy over here and this guy over here? What's going to be the difference in the work done by the thrust force on the left compared to the thrust force on the right?
Wouldn't the data have to be the difference? Because they're both different and one is going down and one is going up.
Well, they tell you that the same thrust force is acting on the plane on the left that's acting on the plane on the right. All right, careful. When we use this formula, this theta right here is the angle between the particular f and the particular distance. So over here, we have a thrust force acting this way, and the plane is moving that way. Over here, we have a thrust force acting this way, the same exact amount of force, the same thrust force, pulling the plane forward the same distance. So if it's the same force going the same distance, and what's the theta in each case? 0. No, because, which way is the thrust force acting? Whoa, that way. Which way is the plane actually moving? Forward. So what's the theta right there? 0 degrees. They're both going in the same direction. So the theta over here would also be 0, because the thrust force, again, is in the forward direction. And which way is the plane moving? Forward.
Then right now we're calculating the work done by the thrust force.
Right now we're calculating the work done by the thrust force. Only the thrust force.
Okay.
And I'm asking you, how does the work done by the thrust force compare? How does the work done by the thrust force on the plane on the left compare to the work done by the thrust force on the plane on the right? They're equal to each other.
Yeah.
So, is the thrust force going to contribute to a difference in work done? No, because the thrust force is doing the same amount of work.
Why is it?
Well, because the thrust force is the same on both planes. The forward distance is the same on both planes. And the theta for the thrust force is 0 for both planes.
So then all we care about is L and FG to see which one's greater?
So far, yeah. Because the
But FG is the same too, so it's acting on it differently because they're going different directions.
well, let's cross that bridge when we get to it, okay? Let's go now and look at the lift force. Yes? They say the lift force acting on each plane is the same. So the lift force is this way. And remember, the plane is moving that way. So what's going to be the theta for the plane on the left between the lift force and the direction of the motion of the plane? It's going to be 90. And what about for the other plane? The lift force is this way, and the plane is moving this way. So once again, what's the theta? 90. Exactly. So is that lift force doing any work? No, because there's no forward component of the lift force keeping the plane going. So how much work is the lift force on the left doing? 0. How much lift force is the plane on the right doing? 0. So does the lift force contribute to a difference in the work done of the two planes? No. So what does that leave us with? Fg, the weight force. Now, once again, the same Fg is acting on both planes. And in both cases, the plane is moving forward the same x, the same forward distance. It's a different theta in this case. They tell you in the problem, it's right on the diagram in the textbook, what's the theta for the plane on the left? What's the theta? 115 for the plane on the right. Right. For both.
This is between the motion that way and the FG.
Right. So let's make a note of that. So only force that leads to a difference in the amount of work done on the two planes is the FG force. So we have the work done by the FG force on the left plane equals FG times the forward x times cosine theta. And the work done by the FG force, the weight force on the right plane, equals FG times x times cosine theta. So in both cases, what was F sub G? 5.9?
Yes.
Times 10 to the fourth newtons. And the distance is 1.7 times 10 to the third. And on this left equation, it's going to be the cosine of 75. Because that's the angle between the force and the direction the plane is moving. It's going to be cosine of 75 degrees. So what does the work done by the F sub G force, the weight force, on the left turn out to be? Could you just give it to me in scientific notation?
I chose not to use scientific notation, but I double checked it. But
2.59.
First of all, is it positive or negative?
Positive.
Positive. 2 point.
Like 2.6.
2.6 times
10 to the
7th
yeah.
joules. And then let's do the other plane on the left.
Is that in meters? Would you put all the 10%?
Oh yes, thank you. That's meters. Thank you.
The other one would be negative 4.2 times 10 to the 7.
Mr. Slazinski, please go to upper E. You have a parent waiting for your appointment. Mr. Slazinski, please go to upper E.
You want to go find her? Okay. So this is going to be times. Just give us a minute, and we'll find a room to go. So this here is 1.7 times 10 to the third meters times the cosine of 115, and what did that turn out to be?
Negative 4.2.
Now, why is this one negative?
Because the work done on the FG isn't affecting it because it's going diagonally out.
Yeah, well, if we take a look, this one here, if I broke that weight down into components, yes? Look. This here would be FG perpendicular. This would be FG parallel. Is FG perpendicular doing any work? No. Because it's at a right angle. In no way is that pushing the plane forward. Is FG parallel doing any work? Careful, it is.
Well,
It's friction.
Yeah, it's like friction. It's in the dead opposite direction. That's why it's negative. But if we look over here and break it down, FG perpendicular, FG parallel. FG parallel in this case is in the direction of the distance. That's why it's positive work. And what are we going to have to do with these two answers that we got?
Subtract them.
Subtract them.